Maybe a word up front. This is a reduced presentation, so because of the time frame, I did hide a couple of slides, which are included in the presentation that I sent you over in a PDF format. So whoever is interested in the details behind it, they are there, but I can't really go through all the slides here in this presentation, time constraint reasons. So off we go. Just a quick word. Luxinar is 25 years old, but in the past it was known as Rofincina. And the latest changes here are not even on the slide, but we got acquired by Tro Group, and we are now teaming up with Irradian Group. And so there is now a joint product envelope starting really from 30 watt. And we are kicking in at 100 watt CO2 power, going up to all the way up to 1 kilowatt. And we also have ultra short pulse lasers currently up to 160 watt. And again, same thing, Irradian, they have a lower power range. So this is actually matching quite nicely. But right now, this presentation is really about Luxinar. And yeah, we have presence around the globe and an installed base, which is actually not an accurate number here, which is way over 30,000 lasers as we speak. But now let's go right into it. Where do we play to our strengths in battery manufacturing? Of course, there's the applications of the ultra short pulse lasers, but other than that, there is everything where you have organic materials, where you have foils, whatever kind of foils, or even the organic liquid that's in the battery. But I have brought two examples here, but here you see a quick rundown on different applications. This is cutting of ceramic coated separate foil on the right hand side of the screen. The left is actually the ultra short pulse notching and slitting of the electrodes. Same thing again, we have on the left hand the LXR series doing surface texturization. On the right hand side, we have another application where we basically decode a battery, and that's the second application we're going to talk today. And finally, we have wiring, we have hairpins, we have bus bars, and we have filler ports. So that's basically all applications where CO2 lasers can be used. Obviously, hairpins and bus bars, there's, let's say, quite a bit of conversation. Let's say there's a challenge between this and fiber lasers, but it's a common application to us. So why use CO2 lasers for batteries in general? There's a lot of organic materials present, which I already mentioned, and there's different wavelengths available for those CO2 lasers that interact with different plastic materials. Those lasers are, they are really mature technology, and so the level of maintenance for these lasers is minimum. Actually, the lasers themselves are maintenance free. You typically have to care more about optical beam paths than about the laser. This laser technology also, it's a gas laser with a sealed gas chamber. The service life is quite long. So we see anything between 30 and 50,000 hours of lasers being in operation, in continued operation. And if you compare it to today's pump diodes and seed lasers, that's quite an impressive number. So this is long lifetime. Also, it's not solid state. It easily competes and compares to solid state technology. And finally, once there's a refurbishment required, the cost of that is very low because you typically need a few optics and a new gas fill, and that doesn't compare anywhere near to if you need a new set of pump diodes. So this is basically a very economical technology. Now jumping directly into the two examples, not limited to the two, but the two I chose for today, which is the separator foils and unwrapping of batteries of prismatic cells. So the separator foils, most of the time today, they are still mechanically cut, but with the introduction of ceramic coated separator foils, there's a major issue with that because first, ceramic introduces a new level of wear to the knives, but there's also, and more importantly, there's the dust contamination of chipped off ceramic parts. So if you move to laser, then you have a non-contact, no wear process here. And the advantage of the CO2 laser over the ultra short pulse laser in that case is simply, again, what we had to review before. It's the low cost and the simplicity. Even if we talk about laser safety, I mean, you need just acrylic or some kind of polycarbonate housing, and you're done with a CO2 laser. So that means this is basically the two levels where it really excels. It is easy to use, and it is improving the economy because it's lower cost. So what we did here this time is we tried to compare 3 different wavelengths on 3 different materials. And in order to compare that, we created an environment where we have same power and, let's say, very similar spot size, not exactly the same, but very similar. So we tried to create a condition where we really have comparable data between 3 wavelengths for 3 different, very typical separator foil materials. And those materials are, yeah, now you basically feel what, so a few slides are missing, but this material 1 is a material where there is a ceramic coating applied. Material 2 and 3 are PE foils, but they are not clean PE. There is a slight part of polypropylene present, and that makes it so interesting for the 1025. But anyway, what all our examples show is that we get at least as good or much better cutting performance with 10.25 microns. So this is something I recommend everybody to look into if he is thinking about coming up with a cutting station, a laser-based, CO2 laser-based cutting station for separator foils. And in this case, the 1025 really, that translates in not only the higher productivity, but you basically get up to 3 times out of, actually even 4 times, depending on the material, out of the same production line if the laser would have been the bottleneck before, if you used 10.6 or 9.3. And at the same time, so you simply, the same cutting process is requiring less energy. So the carbon footprint of that particular process can be improved by simply using a laser wavelength that interacts more efficiently, more effectively with the material. So just a quick wrap up for this application. So we basically saw that the CO2 laser is a reliable tool, easy to integrate in that kind of application, very economic. There is a discussion, or let's say one argument typically is, okay, but solid state lasers have a better wall power efficiency, wall plug efficiency, but it's not what makes the process efficient. Efficiency is how much power do I put in versus the cutting speed. So if my wavelength is more effective than on the material and I can speed up the process there, then it's the overall efficiency that I need to look into, not just the electrical wall plug power. Those lasers have definitely a lower cost of ownership and simple operation. And by the way, since we are discussing this in Europe, I know from firsthand that this is basically already a standard in Asia. So there, the distribution of CO2 lasers within that battery manufacturing facilities and processes is basically much more developed than over here. So little challenge to the European battery manufacturers. Look at this and work with us so we can catch up with what in Asia is already going on. The second process I wanted to show you today is unwrapping of batteries. Why would somebody want to unwrap a battery? We have two scenarios here. One is yield issues of production of battery production, where it's going as bad as up to 30% rejects. And even if that number will come down over time with the growing number of batteries used in the field and coming to an end of life, even after their second life, the demand for recycling will grow. So currently, this is a purely manual process. So that it's really people sitting there with knives, spatulas, scraping and scratching, and then using very aggressive solvents to wipe off the stuff. It's definitely not a process that anybody really wants to do, but this needs to be done. So we can introduce basically an automated process here that does not apply any force to the material, to the thin wall cell housing, and it's creating very repetitive results. And it's basically avoiding dense scratches or any deformation of the battery, of the canister, because that will be reused. Reused if it's from non-conforming cells out of production, and recycled, of course, if it's basically dead batteries after use. The other thing, as we already mentioned, is the change from very aggressive chemicals that are not only aggressive to the user and the environment, but they're also an issue in the when you basically need to dispose them, or not really recycle them, but you need to get rid of them. Let's say it that way. So there's twofold. So it's basically more user-friendly process, and it's a more environmentally friendly process. Not to say that there is not issues, because you evaporate a lot of material, but the key technology here really is it's a delicate process, because if you're working on ready-built batteries and you need to unwrap them and you want to reuse them and rework them, then you need to manage the temperature, because if you heat up the battery more than 80 degrees, then the battery is damaged. So the goal is to have let's say the same productivity of a machine that the workers, the people have, but with less environmentally unfriendly materials, more protective to the battery itself, and basically not damaging the inside of the battery. And that all was achieved. We have there a slide. We always do spectrum analytics of the materials, and that is why we say contrary to the expectations, you see this plastic wrapping would have had a much better absorption, very little absorption anyway, but much better in 9.3 than 10.6. But in the end, that's always one of these surprises. The ablation rate of the 10.6 was simply more efficient and better, so we went with 10.6 here. So yeah, this is basically the outcome. We were near the we were in the low 60s in centigrade, so the cell was very safe, and it was no problem. The productivity was very comparable to the hand scraping, and the power level we used was actually a 450 watt laser here. And the one thing that doesn't work, you don't get a totally clean surface with CO2. there was a very, very thin sticky residue left, but that was easily wiped off with a little bit of isopropanol, so a very mild solvent compared to what they typically use. And that could be also fully automated. So this whole thing from removing the wrap to removing the residue could be an automated process. So what's the conclusion then of this process? We can create a more environmentally friendly, I would not call it a very environmentally friendly process, but a less environmentally harming process. Definitely much better for operators. That's definitely a major improvement, and it will give you repeatable results and basically avoid more rejects because of mechanical forces and tools are basically applied. Definitely one thing is the fume extraction. You evaporate all this, so you have to make sure you have a good fume extraction and adequate filtering. So basically that remains of the process will will accommodate in that filtering. Then there's let's say a finishing process left, but in the end, the total process is much more beneficial compared to what is done today. And with the growing demand of batteries, even if the yield improves, there will be always batteries right out of production that need to be reworked. So this is then a measurable and a controlled process to basically cycle those back into production. And then, we are here with the epic questions. Well, what can we do for you? We refer to a database of about 3,000 different applications. And if you have questions about can it be done, what is required, I think it would be a good step just to see if we have something already, or if not, then we will do application or process development work with you. And that also is funneled in a long experience of system layout, how to basically make that laser work in sense which beam delivery, what beam steering. So we can basically guide you the way to a laser machine, or help you with the selection of a laser integrator that will build basically the best possible machine. What can you do for us? Well, of course, speak to us. Whenever you see organic materials, then please think about the good old CO2 technology. It's old but good, and it's still out there and needed. So yeah, we would be happy to talk to you. And with this, thank you very much for your attention, and I'm here for your questions.